And this is important because now in the following, I'm about to show you some results for band structure calculation. And I have to tell you that for all the results that I'm going to present, we use this two-dimensional model with isotropic assumption. Okay. I just establish my own. Okay, so all the band structure calculation that we perform have been achieved using the Kegel-P theory. Now, I'm not going to go through detail of the Kegel-P theory since if we take the rest of the day. I'm sure we don't want to meet the reception later. So I'll just give you some very, very general features just to make understand what we need. Basically, the Kegel-P theory has been developed first for the band structure. The starting point is the single particle Schrödinger equation that we have in the most general form with the kinetic part and the crystal potential. Basically, what we have to solve in the Kegel-P theory is an eigenvalue equation for the wave function and for the energy we are interested in. And usually, at least for bulk structure, B should reflect the periodicity of the material. But now we want to apply this model to quantum dot heterostructures, so there are some relevant differences. So basically, you can say that we have only a local periodicity, since we have different crystal structures in different materials, and so generally B is unknown, so we can have an exact solution. There are different approaches to apply Kegel-P theory to quantum dot heterostructure. Basically, for our model, we follow the exact envelope function theory as developed by Barth and Foreman. Again, I'm not going through details, but the general idea is to expand the wave function in a set of periodic UN functions of the homogeneous system, in this way, an expansion where phi are the envelope function, which are the solution of an infinite set of coupled differential equations. So basically what we do is, the theory what we do is to insert this in the Kegel-P equation and then we derive this infinite set of coupled differential equations. As you can imagine, it's quite difficult, it's impossible practically to solve a set of infinite equation. So basically what we do to reduce this set, we choose only a finite set of them, UN, to be solved exactly, and then we try to write as a perturbation. So depending on how many bands we choose, we have different models. So again, here I write the wave function for our, in this case, bound state for the quantum dot. We have this expansion here in the periodic set with the envelope part. And basically we use two different models. So if n is equal to 1, we have the one-band model, where we use the x function for the conduction band and the heavy load for the valence band. And then we have n equals to 8. Well, apart from these two bands, we have also the light band and the spin-off. And since they are all twice degenerate, we have the 8 band. So basically, as I said, we have to solve the eigenvalue problem. So we have an eigenvalue equation for the envelope functions here. This is the most general form for the Hamiltonian. Obviously, the specific form of the Hamiltonian depends on the model and on the structure. But generally, what we have is an Hamiltonian given by a sum of the kinetic part, of the energy of the unstrained band H, and of the strain-dependent part. We solve the eigenvalue problem, then we find the wave function of the bound state and the energy level. And then we can use this information to calculate, to analyze some of the optical properties of the dot. So basically, what we calculate first is the momentum matrix element, P and M, that you have here. This is the momentum matrix between the states, confined state N and M. And basically, using the fact that the envelope function is locally varying in the crystal, we can split in two parts. We have the envelope part here of the momentum matrix, and the block cell part here, which is basically by this atomic part times the overlap of the envelope function. And so here we have these two components. In general, it is quite common to consider only the block part, since the envelope part is at least one order smaller than the other. And also our results confirm this point. So we only use the block part for our results. And then from the momentum matrix element, we can derive the dipole moment here using this relationship. Here we have the momentum matrix and this connection to the dipole moments mu and m, which is in the same state. M0 is the free electron mass and E is electric charge, and basically we use the energy difference in this way here. We do like that because we know that to calculate directly the dipole moment between the block cell part is meaningless since they are basically non-localized states. So we first calculate the momentum mass and then we derive the dipole moment. So this is the theory, and then we apply this to a different set of indium arsenide, gallium arsenide conical quantum dots. We study different sets of this structure, but basically the results I'm going to present, which are the most interesting, are with a fixed aspect ratio when the radius is 2 times the height of the dots. We are interested mainly in investigating the combined effect of band mixing and strain on the optical and electronic property of these dots. And as I told you before, we use this two-dimensional isotropic, with the isotropic assumption model for the strain part. And so we disregard piezoelectricity and atomistic aspects in this calculation. So here I'm going to present the first result. Okay, what we have here, we have the results for the first 2 models. On the left we have 1 band model without strain. On the right we have 8 band without strain. So these are the 2 models without strain. On the top part we have the confined state. We focus on the first 6 confined levels. Basically every level is twice degenerate because of the spin, and in the 1 band model we also have a double degeneration because of the geometry. Here you have the 5 strongest transition, the 5 strongest dipole moments indicated, and also the width of the Harrow is proportional to the strength of the transition. And in the bottom part of the figure, you have for these 2 models the value, the magnitude of these dipole moments. And here you have for 1 band model they have in this decreasing order, and then we put here for the 8 band model in the same order as they are here. You can see that there is a lot of difference between the 2 models, both from the qualitative and also quantitative point of view. And this was quite expected since we know that the 8 band model completely changed the density of the state, so we also have much more state in terms of 1 band, and also when we calculate the dipole moment, we have to consider that we have all the contributes of all the possible combination of the components of the wave function. So in this case, we have 8 components, we have to consider the sum of all the possible dipole moments. So the fact that they are different was quite expected, but what is very interesting is to compare this slide with the following one, which gives the result for the same 2 models but including strain. If you compare these 2 slides, you can see very clearly that if you look to the dipole moment that you compare with the previous one, you can see that now if you introduce the strain, they look much more similar than before. Basically we can see that there is a very good qualitative but also quantitative agreement between these 2 models now if you introduce the strain. And that's very interesting because this is given to the because of the effect of the strain on the different components of the wave function. Because in the case of the 8 band model, we have a wave function which is a sum of all 8 components. Basically, we can say 8 heavy hole and light hole. And the effects of the strain of these components is different. So basically, what we have is because of the strain, that we have a splitting of these 2 components. So we can say that the ground state and the first excited state, because of the strain, are much more heavy hole-like than before, that without the strain in this case. And that's the reason of this agreement between the 2 models, which is the 1 band where we only have heavy hole. The second thing that we can notice is that we have a reduction of the strain of the transition. You can see that for both models, introducing the strain, we have a reduction of the strain of the transition. And this is again a combined effect of strain and band mixing, because this is given basically by the effect that the strain has on the wave function. If we can see here looking at the probability density of the valence band ground state. I show you the valence band ground state because we know that in the case of the conduction band ground state, we only have the aspect in this model of the hydrostatic strain. So what we have is basically a shift of the energy. But in the case of the valence band, the situation is more complex because of the axial strain, which is quite inhomogeneous in size of the dot, we have a strong effect on the shape of the wave function. Here on the